All right, so as we go take a look then at Chapter 2, as a quick reminder, Chapter 1 was all about the Rutherford model of the atom. And in this case, Rutherford's model had this tiny little nucleus in the middle with this large electron cloud around the outside. And inside the nucleus, we saw this is where the majority of the mass of our atom came from, because we had our heavy protons and slightly heavier neutrons crammed inside of this tiny little nucleus. And he came up with that based on his gold foil experiment. And so he postulated then that around the outside of the atom was the electron cloud. And that this is kind of where all of the electrons inside the atom were found. So in order to get a better understanding of what this chapter is going to be about, which is mainly focusing on this electron cloud, we have to get an idea of how quantum mechanics works, because this chapter focuses on the quantum mechanical model of the atom. And quantum mechanic model of the atom is based on observations of emitted light. So our first video then is not going to be about the atom itself, but it's going to be about some of the observations on the mechanics of light. And when I talk about anything regarding light, I'm talking about electromagnetic radiation. And all this means is that light is going to be treated as a wave. And so in this case, a wave has the same oscillating behavior. And we're going to talk about simple waves first, and then we'll talk exactly what this electromagnetic wave means with regard to light. So we'll characterize a wave by three things. This first piece right here is this variable lambda. And this variable lambda corresponds to the wavelength of light, or the distance between two peaks. Some of the other important pieces regarding light are this amplitude, which corresponds to the height of the wave, and then lastly, we often use frequency to talk about waves, because in this case, frequency says the number of times the wave repeats. And it seems pretty intuitive that if I have longer waves, I probably won't be able to get as much repetition. So when we talk about this, we'll see that there's a relationship between frequency and wavelength. And we'll see that this relationship is defined by the equation c equals lambda nu. So in this case, c is a constant because it's the speed of light. Which is equal to 3.00 times 10 to the 8th meters per second. We know lambda is the wavelength, and in this case, my wavelength has to be my measurement in meters. And then lastly, I know that my frequency is the number of repeating cycles. So in this way, we measure it in hertz, which is just a number of inverse seconds. So when you multiply wavelength and frequency together, you end up with units of velocity. So when we take a look at this, the reason we care about wavelength and frequency is because there's actually a practical application for each of these pieces. When I talk about the wavelength, we talk about the color of light that we observe. You can also see this classify the type of radiation that we have as well. Amplitude talks about the intensity. So if we're talking about light waves, this corresponds to how bright or how dim my color is. And then lastly, frequency has a lot to do with the energy associated with the wave. So if I have, let's take a look at an example real quick. If I have a wavelength inside of like a red barcode scanner. When I look at the wavelength, I'm going to calculate the wavelength of that barcode scanner. By looking at the frequency. And the frequency is 4.62 times 10 to the 14th hertz. And we want our wavelength in nanometers when we're done. So what I'm going to do is I'm going to take my C equals lambda nu, and I'm going to plug in the pieces that I know. I know C is a constant, and that's always going to be 3.00 times 10 to the 8th meters per second. I'm solving for lambda, but I do know the frequency. And so when I divide both sides by 4.62 times 10 to the 14 hertz, we end up with the value that is close to, hang on, let me get my math. After doing the math, we see that lambda comes out to be 6.493 times 10 to the negative 7th. And that comes in meters. So then I have to build my equivalent between meters and nanometers. 1 nanometer is 10 to the negative 9 meters. And so when I multiply this through and build my bridge, I end up with the value of 649 nanometers. And so that's really all there is to it. We can use the wavelength of light to help us characterize what types of colors, if we're in the visible spectrum, or what type of energy that we're going to absorb. So when we take a look at the EM spectrum, we're going to see my frequency, or my wavelength, starts off around 10 to the 5th through 10 to the negative 1st meters. This corresponds to what's called a radio wave. This is the wave that's used when we use like radio communication. We also use this for like some of our TV waves and some cell phones for communications. Anything between 10 to the negative 1 and 10 to the negative 3. This corresponds as a microwave. And we'll see that this corresponds and keeps getting even lower. 10 to the negative 3 meters down to 10 to the negative 5th meters is where we talk about infrared. In this case, like IR radiation. And then right between here, we see it's around 10 to the negative 6, actually. Sorry about that. This is where we have our visible light. And we'll see that my reds are closer to 750 nanometers, and that our purples are down around 400 nanometers. And then from there, we start getting a little bit smaller each time. So we're around 10 to the negative 7th, between to 10 to the negative like 8th and 9th. It's where we have X-rays. And to keep going a little bit, we then have our last one where we have 10 to the negative 11th, all the way down to the 10 to the negative 15th meters. And this is where we see things like gamma radiation. So when we're taking a look at some of these values, we're going to observe that we have different types of radiation based on their wavelength. So when we take a look at electromagnetic waves to begin with, then, we'll see that they actually have two components. An electric component that I'm going to draw here in green. And my electric component generally is in the vertical plane. And in here I'm going to show a purple component, or a purple wave, that kind of goes perpendicular. And I'm going to represent that we're perpendicular by using dashed and wedged lines. My wedged lines show that I'm coming out of the page. My dashed lines show that it's going back into the page. And an important detail here, so like here's the main axis we're traveling along. We'll see that the purple's the magnetic component and green is electric. And this means I just have two types of waves at once. So when we have this set up then, we'll see that the electric component is perpendicular to the magnetic component. This will be a little bit more important when you get into physics, but I wanted to go over this real important piece. In this course. So then, when we talk about different waves of light then, one of the big breakthroughs that showed that light was indeed a wave style nature came from the idea about interference and diffraction. So in this case, we talked about if I have one light wave, but what happens if I have two? So let's take a look at an example real quick. In this case, when we talk about interference, we talk about how two waves combine. And there's really two extremes that we're going to be looking at for this. We're going to see that there's constructive interference, and that there is destructive interference. When we take a look at constructive interference, I have two waves whose wavelengths line up perfectly in phase with one another. So in this case, my peaks and valleys line up perfectly. And what happens when they combine is I get a wave with twice the amplitude. But with destructive interference, instead of combining together, my destructive waves are going to be offset from one another by half of a wavelength. So that means instead of starting up, they might start down. And I see that my peaks and valleys kind of line up, and when we add them together, they cancel out. So in this case, in constructive interference, my signals combine, whereas in destructive interference, my signals cancel. And the way that this was figured out was because what ended up happening is we would take a beam of light and we pass it through a narrow slit. And so the thought was, if light behaves like a particle, we should see that when it passes through, we'll only expose a small amount of the paper. We'll only see the color appear on that spot. So this is what we would see if light behaved like a particle. But what we observed is that light behaved a lot more like a wave. So when I took that same slit and I passed my light through it, we ended up seeing this emitted pattern. And I would kind of see that there's like this diffracted wave that kind of expands out from our small slit. And so this is kind of like how a small pinhole camera operates. We see this tiny aperture right here that we expose for a certain amount of time, and then we allow the diffracted wave to come in and make our picture. And the big thing that proved this destructive and constructive interference was the really famous double slit experiment. So in this case, what ended up happening is they passed light from our light source here through these two waves. And what ended up happening is that on our film over here, we saw that we kind of had these regions where light would get intense and then it would decrease. And so only certain spots of our film was exposed. And so we would say that if we had a constructive interference, if we had a constructive interference, this is the area that was exposed to light. And one thing that was really interesting is that whenever we had destructive interference and we had no exposure, that this distance between the most developed and the least exposed was equal to half of a wavelength. So this distance here was half the wavelength, which only further goes to support our constructive and destructive interference, because these are out of phase by half of a lambda. So this was a really big deal back in the day, because in this case light was thought to be a wave and only a wave because it behaved according to wave properties. We saw that this was a wave mechanic. So when we then started doing some additional experiments, there was something called the photoelectric effect. So the second important piece here was revealed to us by the photoelectric effect. And this was a really interesting phenomenon. So what happens, and this is still kind of something that's used today in a tool called a spectrophotometer. Effectively, what ends up happening is that if there's a strong enough potential, you can observe that inside of a glass tube called a photomultiplier tube, this is a way to enhance a light signal. You'll see that there's kind of like this large metal piece right here, and there's a small electrode that runs up. What ends up happening is we connect this to a positive side of a big old battery. Pardon my janky drawing. See if we can do a little better. There we go. And over here I have this negative side hooked up to an ammeter, or something that measures current. And so effectively this means that we have a negatively charged electrode on one side of the tube and a positively charged electrode on the other side. This was kind of an interesting phenomenon, because one thing that happened is with this photoelectric effect, whenever they shined light on this negative piece of metal, electrons were liberated to the positive electrode. And so what was really cool is that when we took a look at the frequency of light, and the rate of electron movement, so in this case the current, they saw that at low intensity light, there were fewer electrons liberated than when they used a high intensity light. But one thing that never changed was that the frequency of light didn't change between when electrons would be ejected. which was kind of cool. And so they said, yeah, light behaves like a wave, but we can count it like a particle. So in order for this to come across them, they said, all right, based on the current and all that other good stuff, they came up with this relationship then that said, okay, then the energy has to be equal to some constant times the frequency. And so what this allowed us to do is then now start thinking about light as not only a wave, but also as a particle. And this way we can kind of count it. And a particle of light is called a photon. And so this energy is the energy of one photon. H is Planck's constant. Max Planck was the guy that did all of the work on this in terms of light as a particle, and it's equal to 6.626 times 10 to the negative 34th joule seconds. And then frequency is in hertz, or 1 per second. So when we take a look at this, we can also make one additional substitution. If you'll remember, we can also, there was a relationship between lambda and nu. So what we can do is we can substitute nu for c over lambda, and we can rewrite this energy equation not only in terms of frequency, but also in terms of wavelength. And again, some important things to consider here. My lambda is in meters. C is 3.00 times 10 to the 8th meters per second. And h is still Planck's constant. And again, the energy we're calculating is the energy of one photon. So what we can do with this is we can characterize a couple different things. We can determine the energy of a pulse, we can determine the wavelength of light that comes out, or we can determine the number of photons that we get. So in this case, what we're going to do is we're going to take a look at an example of how to determine the number of photons. So in this case, a laser made from nitrogen gas with a wavelength of 337 nanometers contains 3.83 millijoules of energy in one pulse. How many photons are in that pulse? And the way we figured this out is by taking a look, and we're going to go from the energy, we're going to go from the wavelength to figure out the energy of a single photon, and then we're going to use the to see how many photons we get compared to the energy that we measure to get our photons. So let's take a look at this. I have an energy of a photon equals hc over lambda. So I'm going to plug in my variables, and this is 6.626 times 10 to the 34th joule seconds. There's my h. C is 3.00 times 10 to the 8th meters per second. And my lambda is 337 times 10 to the negative 9th meters. So I kind of cheated and just plugged in my nano. So let's take a look at what this looks like when we do our math. 6.626 e to the negative 34th. It's a negative there, that's going to be important. Times 3 times 10 to the 8th divided by 337 times 10 to the negative 9th. And so in this case, I know that the energy of a single photon comes out to be 5.8985 times 10 to the negative 19th joules. And again, this is of one photon, so I can even label this as joules per photon to help me out with this. I'm also going to put a little line under that 9 to help remind me where my significant figures need to go. So now what I'm going to do is I know 3.83 millijoules. This is the same thing as saying I have 3.83 times 10 to the negative 3 joules. And I need to figure out how many photons that is. So I'm going to take my one photon and put that piece up top. And I'm going to use my number on bottom, 5.8985 times 10 to the negative 19th joules. And we'll see what kind of value we come up with. When I do my math, I have 3.83 times 10 to the negative 3 divided by 5.8985 times 10 to the negative 19th. And so this gives me a final value equal to 6.49 to 3 significant figures times 10 to the 15th photons. So we can figure out that's how many equivalent particles of light we had inside of our energy pulse. Very good. So with this gives us enough of an understanding about the basics of light. And in this case, we can take a look at one packet, one photon of light, one single particle, and use it to describe it by using the wave nature of light, using its wavelength, frequency, and amplitude. All right, so what we're going to do in our next video then is take a look at some of the important breakthroughs that led to the quantum mechanical model of the atom.